In this video I wanna talk about the latest changes to my oversampling test repository, where I always put the current state of my personal oversampling implementation. And the purpose of this thing is to have an alternative for Juice projects, because in Juice you have to use the Juice DSP namespace, which uses the Juice audio block object very extensively throughout the sole namespace if you want to have oversampling. And if you have already made a project and it's got pretty big and it has audio buffer all over the place and not audio block, and then you find yourself wanting to add oversampling, then you sometimes have to rewrite a lot of stuff to make it work with audio block instead. And because I found that a little bit annoying, I decided to make my own oversampling implementation, and also because I just wanted to know how that works and everything. And that's of course not news if you know my channel, and you know that I've started this project a while ago, but it got a little bit better because in the process of developing and rewriting my vibrato knell, I also used oversampling, which you can turn on in the audio settings. And now I copied the current state of the oversampling class from knell back into my generic oversampling repository, so that everyone who wants to take a look at it has not such a hard time looking at it than as if they had to go into knell and, navigate the whole project. Now, first of all, let me run this code a little bit so that you can have more of a practical view about it. Alright, I have to turn on the microphone or I will hear myself. Now, when you run the oversampling test project, then you get this little audio plugin as a standalone currently, where you can turn off and on oversampling. And this will have some discontinuities because it reallocates a buffer, but it does so in a hopefully safe way. And then it has a bunch of generic DSP processors to test how good the oversampling acts, like a wave folder that you can dial in, a saturation that you can dial in, vibrato frequency, vibrato depth, and gain that you can dial down with all these things, or up. But I actually never have to put it up. And that way you can test if the oversampling is good, and you can run other audio through it if you want to, or you can add more DSP modules because the project's not very complicated at the moment, so it would be easy to just add your stuff to it. Basically, it has a header called nonlinear DSP, where I have put all the things that I used to make little DSP modules. You see, that's pretty comfortable. And then there is the oversampling folder, which has a header for the convolution filter, a header for the IIR filter, and a header for the DSP processor of the oversampling class in general, with a little to-do list what I want to do. In the plugin processor, I have an instance of the oversampling class, a bunch of DSP processors, the audio processor value tree state, because I decided to take it easy in this project when it comes to parameters, and the pointers to the individual parameters. In the plugin processor, I'm instantiating all these things. The oversampling class wants to have a pointer to this Juice audio processor. Now in prepare to play, oversampling gets the sample rate samples per block and returns another or the same sample rate depending on whether it's turned on or off, so that all the upcoming stuff can work with that. And also you're adding to the latency, whatever latency you have, until you reach the point where you can say, yeah, that's the amount of latency that I want to send. Actually, I think you gotta be more careful with this than I did it here, but I'm not exactly sure. But if the oversampling is currently oversampled, or turned on, then I guess the latency that is returned from the vibrato should be like a little bit higher than what you would put in here, since the vibrato works with a whole sample rate. And then you would do something like oversampling get oversampling factor. Yeah, that would be more reasonable. And because the set latency samples is not oversampled, so it wants to have the unoversampled latency. Now process block is basically the same as always. Then num channels in and num channels out is captured, and then we can start the upsampling process. Oversampling, upsample, you put in the normal buffer, you tell it how many channels you have in and out, and then if it gives you a null pointer, then that means that the oversampling state has changed, that we are not on 1x or 4x anymore, but the other one. And that would mean that we now put actually in this case I decided to just say then okay, then let's just use the normal buffer and don't oversample here. And the downsampling at the end, I'm asking if the buffer upsampled is a different buffer than the buffer downsampled, and only then we downsample, which makes sense, because only if these are different buffers, then it makes sense to actually downsample. Now I'm currently wondering, no, these are both pointers, so this is a very fast compare. Yeah, so that is basically how it works. Now num samples, you have to if you had a num samples variable in your process block before, you have to update it with a new num samples in case that it's another num samples now with a new buffer. Then you get the samples from the buffer, and then your processing can start. And at this point I can show nicely that there are different ways to go about that. Like the vibrato that just asks for a float pointer of samples of just one channel, and you can do that easily and pass on num samples as well. But you could also write structures where you just input the audio sample buffer, because the upsampling thing just handles making the internal audio buffer have the correct value for num samples. So even if you write your methods not in a way where you have to pass on a variable for num samples, it will just work, which is a workflow that I came up with because I feel like that's nice. Also, this project has a little example for something that is not part of the oversampling process, like this gain applying thingy, which just comes after the process, because no matter what happens here, at this point it's the normal buffer again that does the thing. And there are also other examples for such processes, like mid-side encoding, where you would put the encoding before the oversampling and the decoding after the oversampling, because that's just not a process where oversampling will ever make a difference, except a negative difference in performance. Now, I think that's all that you have to know about how the way it is implemented. Now about the way it works. Yeah, you just make an instance of the processor, and basically this is the copy constructor, not very interesting, but this is a normal constructor, so it gets the audio processor, and there are some magic numbers in here, and yeah, I'm aware that magic numbers are not cool, but that's just something that I went with. Now the thing is, these are two different types of filters that I made. A convolution filter and a low-key Chebyshev filter. And the convolution filter are the up and down filters for the 4x, and the low-key Chebyshev filter are the up and down filter for the 2x. So the initial and more important filters are IIR filters, and this is an FIR filter. And the reason for that is, if an FIR filter has a very wide slope, or a very narrow slope more like, so a very a very short passband in DSP terms, then it has a lot of samples, and that is bad for the performance. And since I'm not a magician at DSP programming, my performance was really bad in the last state of the oversampling class. So now I only use convolution for the up and down sampling from 2x to 4x, because there you can be a little bit more sloppy with the slope, and these settings give you a slope of only 17 samples, which performs just fine in my opinion. And then the up and down sampling filters of 2x, they just want to know the number of channels. And then some other stuff, like this is important for updating the oversampling class. I think I made another video about how I implemented that. But basically, while being in the upsample process, I'm checking if the thing wants to update, and if yes, it calls prepare to play of the audio processor, which obviously reallocates everything. And then we can return, and then we go on if we want to with this upsampling process or not. And yeah, the upsampling process, it just works just the same as it worked before. I don't know if I should go into it too much in this video because I made another video about it already. But basically I'm preparing some variables so that I can work with that for 1x, 2x and 4x. And then, okay, this may be interesting because someone in the Juice forum lately made a question whether or not you can resize a buffer in process block. And yeah, that's possible, but only if you use these settings. Keep existing content true, of course, because you want to resize something but still have the numbers from the beginning. Or actually, I think it doesn't matter if you keep it because you're overriding it anyway in this method. Yeah. So this one doesn't matter. Clear extra space false, of course, because you will not need any extra space. Because in prepare to play you already put the buffer to a size that is bigger than this size or equal to num samples 4x. But it will never be bigger. So this also doesn't matter, but what matters is avoid reallocating. Only if this is enabled, then this method is being saved to be called from process block. And that's why, but it's also important because only if you do this, then the buffer will have the correct number of samples if it's upsampled. And that's a shame because this method goes through tons of if statements just to change the variable num samples. And I guess that is the reason why Juice at some point decided to go away from using Juice audio buffer and just made this audio block thing because it handles these kind of situations better. But my project was just very far ahead already and I did not want to rewrite everything. So I did it like this. But of course, for future implementations of stuff, I might just either write my own buffer or actually use audio block, because I did test this thing in another project and it felt quite okay in most cases. Now anyway, upsampling to 2x with this method and then upsampling to 4x with a very similar looking method but looping backwards. I don't want to explain that now because one should look at it very closely anyway to understand it and not just listen to a voice. And then there is some channel handling if input channels are smaller than output. That is actually something that I did not have in my first implementation of oversampling, but it just came to me while developing Nell because at some point I realized it did not work very well on mono tracks, and then I figured out all the different channel configurations between mono and stereo to mono and stuff like that. But there are no other channel configurations that I support with this implementation, which is okay in my opinion because I feel like most stuff is just stereo anyway, and as a musician you don't want to fiddle around with surround anyway if you are not a film music maker. And also, if you have any mid-side processing in your plugin, then how do you want to convey this information in the UI anyway? That there can be mono or stereo with mid-side, or surround with not mid-side again, but then what is the equivalent of mid-side and surround? I don't know. Probably nothing. So let's just skip everything else that is not mono or stereo. Then here downsampling twice and then channel handling again. So in future implementations I might outsource the channel handling to some other place in the code. So because I noticed that every class sort of has its own channel handling and sometimes it looks very similar. So this might be a dry violation here. I have to figure that out some other time, but it works. And there's also an implementation for process block empty. And this thing also returns something, which is just a bool. And it returns true if the state of the oversampling has changed, and else it returns false. So that in process block bypassed, you can use this method to find out if you have to update anything also. Yeah, get sample rate, upsample, these are some getters, here are some setters. This can be called from the message thread to put wanna update to true. And this is how to get the latency from the filters. And at the moment this method is a little bit silly because IIR filters technically don't have latency, but I think you can get a little bit closer to null if you just fiddle around with it a little bit. But I have not managed to find out an exact calculation of how to reduce the null exactly yet. So that is something that I'm not very happy with yet. And everything else I think is alright. Now there are some other to-do list things, like trying different filter types for just the processing itself. Like I was suggested polyphase IIR filters, half-band polyphase IIR, I don't know if that's the same in this case, and Butterworth. I think what I did is already a Butterworth. No, it's Chebyshev, yeah. I still have to figure out what that all means and which benefits that holds, but this is just the implementation that I currently have. Also, I want to implement automatic reaction to different sample rates, because say you have a sample rate of 44.1 kilohertz, then you would need a steeper filter at the beginning than as if you are already starting at something very nice like 48 kilohertz or 88.2, where you can be very sloppy even on the first filter already, which would be a performance gain, of course, so we could use that. But I did not implement it now yet. It's just a very straightforward implementation that works for 44.1 and everything higher, but it always has the same amount of work to do. Also, I was suggested to use more SIMD instructions for optimization, but I'm not so much into low-end C++ yet, so I just put it on my to-do list for some other time. Now, changes to my IIR class. No, the convolution class, that was the state of the oversampler the last time that I released it. So basically just a little code cleanup where I use this a lot, using something equals something else to have a little bit less convoluted code afterwards, like in this impulse response, but apart from that, it still does the same. Then there is this powerful method for creating any type of FIR filter from a sample rate and a frequency and a bandwidth, and the fact whether or not this is for upsampling or downsampling. What was the difference? Oh yeah, they have different target gain. Alright. Now convolution, it's basically just a filter for one single channel, and I'm not even sure if I use all of these methods still, because some of them turned out to not be very smart, I think, but I just keep them here until I figured out which ones were the ones that didn't make it into the implementation. you can check them out if you want or not. Convolution Filter, which is just basically, well, it's just multiple channels of convolution. Actually, I could make this an array because I decided to go with only stereo anyway. But I won't do that now because I just want to release this now. And yeah, I guess that's a change that will come into the next version. And IIR filter is a new header for the oversampling class that has an IIR filter which has I think that's a 6-pole one, or is it 8-pole? Wait, 1, 2, 3, 4, 5, 6, 7, 8-pole. Okay, but I'm not sure if all of the poles are used currently. No, just 4 poles are used. So technically, I should make another IIR class that does not use the other poles, so that I can reduce this function a little bit more. But I guess the optimizer of the release mode would optimize it away anyway, I hope, because they are 0 all the time anyway, so it should figure out that it can be deduced away. But if not, I don't know, I will probably change that too in the next implementation. But that's just something to look out for. If you think that the performance is still not good enough, maybe try that. And this struct has one little low-key making a Chebyshev low-pass filter method with very specific settings. A 4-pole low-pass with its frequency at almost the end and a very specific amount of ripple. And there are these magic numbers. And I got this from the dspguide.com website, where you can learn how to make IIR filters and Chebyshev filters. And there are different ways to learn that on that page. And I started off with a low-key approach, where you just steal some magic numbers and plug them in. And that works. But I gotta say, this IIR filter, it does change the flavor of the sound a little bit in the high end. It makes it slightly more muffled. So some people might think that this is not good enough for their oversampling implementation. It does perform very well though, so I am very happy with this for now. And then I try to implement some other method from that website. Maybe I should go there and just quickly show you what I mean. On one day I felt very adventurous because I went to that page with this filter, recursive filters, and I think it was one of the last pages of this that had this terrible method. Oh, it was a Chebyshev designing the filter, maybe. Yeah, that was where I stole the numbers from. And then there is some method for, yeah, this was it. So there is some method in a very peculiar looking old programming language for making your own Chebyshev filters. And I just tried to learn this language and write it down to also work for me. And the result of that is this struct that that basically tries to do exactly that. And if you want to try that, you would just have to uncomment this and instead comment out this. And then it would use the make Chebyshev struct to attempt to make this filter. But I felt like it didn't work because I got different results than the ones that are proposed by this website. And the results also looked kind of like a filter, but they were just different, so I didn't trust it and didn't use it in the end. I should revisit this idea though, because it's actually quite cool, because in the end it would also let you make your own filters with these settings, just like the Fear one that works very well, but with an IIR filter. And you know, IIR filters are much more performant, so it is very beneficial to have something like this, and that's why I want to revisit it at some point. Apart from that, the low-key Chebyshev filter is just working just the same as the convolution filter. It has the two filters, and then it can process the block and stuff. Then it just does its thing. Yeah, I think that is enough for this video. If you want to know how it performs and how it sounds, and if you liked it, then you have to try it anyway yourself. In the description I will put the link to my repository so that you can just go there and try that. See ya.